Today we are going to talk about activation energy and catalysis. Okay. Now, you studied before what is activation energy, and we said that for any two particles to react together, they must collide first with energies enough to form the product. And this energy by which the two particles must collide together is called the activation energy, and we denote it by EA. It means activation energy. The activation energy is the minimum energy by which two particles collide together in order to be able to form a product. Okay? Now, when these two particles gain this kinetic energy, if these are the two particles that are acting here as the reactants, when they gain this enough energy, which we call it the activation energy, they form what we call the transition state. And from this transition state, they start to form the products by releasing energy and forming the products, whether they are going to form an exothermic reaction, as you can see here in this figure, where the energy of the products is lower than the energy of reactants. And even if it forms an endothermic reaction, where the energy of the products is higher than the energy of reactants, also the reactants must collide together with a certain amount of energy, which is called the activation energy, and the transition state. And after the transition state, energy is released to form the products, whether in an endothermic reaction or an exothermic reaction. Okay, so this is called the activation energy, which is the minimum amount of energy required by the reactants in order that when they collide together, they can form the products. Okay, now we talked about in the AS course, we said that we can use what we call catalysts, where catalysts are substances that are able to increase the rate of the reaction without themselves being used up. We took this in the O level and the AS, that catalysts are substances that increase the rate of a chemical reaction without themselves being consumed up. And we also took in AS course that the catalyst would decrease the activation energy needed for this reaction to take place. If the original activation energy was here, this amount of activation energy must be used by the reactants in order to form the products, then the catalyst would lower this activation energy. Instead of this high activation, only a small amount of activation energy will be needed, where catalysts provide an alternative. Catalysts provide an alternative path route, by which the reaction goes by. So catalysts provide the reaction mixture by an alternative path route for the reactants in order to form the products. And this alternative path route must be with lower activation energy. Instead of climbing all this mountain, then it has only to climb only this small mountain in order to form the products. So this is the main function of the catalyst. Catalyst speeds up the reaction or increases the rate of the reaction by providing an alternative path route to the reaction mixture in order to form the products in a minimum amount of time. Now, we have two types of catalysts. We have homogeneous catalysts and we have heterogeneous catalysts. Of course, from their names, homo means like each other, and hetero means not like each other. They are different than each other. Now, homogeneous catalyst means that the catalyst has the same phase as the reactants. If the reactants are in the form of solids, then the catalyst is a solid. If the reactants are in the form of a liquid, then the catalyst will be in the form of a liquid. Aqueous solutions, it's in the form of aqueous solution as well. Gas, then it's as a gas as well. So here we call it a homogeneous catalyst. It means that it has the same phase as that of the reactants. As examples of homogeneous catalysts, if we take this reaction, propanone aqueous plus iodine aqueous, to form the iodopropanone aqueous plus hydrogen ion plus iodide ion, here the catalyst used is the acid aqueous. It's a hydrogen ion aqueous. Hydrogen ion, as we know, represents the acid. So here we place an acid. For this reaction to take place, we put an acid acting as a catalyst. And since it's in the aqueous state, just like the propanone and the iodine, then we call it a homogeneous catalyst. Another example, if we take, for example, here, the difluorocarbons, when they are present in the upper atmosphere, the ultraviolet light decomposes this compound, forming a free radical, which is the chlorine free radical, and leaves the chloro-difluorocarbon as a free radical as well. This happens in the upper atmosphere near the sun. And then the chlorine free radical will decompose the ozone layer. That's why nowadays the difluorocarbons, or we call them the fluorochlorocarbons, they are now banned. They are not used at all nowadays, neither in refrigerators nor in aerosols or whatever, because this reaction happens in the upper atmosphere near the sun, where the sun provides the energy enough to break the carbon-chlorine bond, forming a chlorine-free radical. And then the chlorine-free radical would decompose the ozone layer, where the chlorine-free radical is in the form of a gas, and the ozone is also in the form of a gas. It decomposes into ClO free radical plus oxygen gas. And then the ClO free radical in another step reacts with more ozone to form 2 oxygen molecules and chlorine free radical. So as you see here, the chlorine free radical entered at the beginning of the reaction, and it went out at the end of the reaction without being used up. Although during the reaction, it has a function. It has a place to be formed, where the chlorine free radical reacts with ozone to form ClO free radical. It didn't stay as a chlorine free radical only, but it reacted with ozone, forming ClO free radical. But at the end, it came out from the reaction as it is. That's why we call the chlorine free radical as a catalyst, because catalyst enter the reaction and comes out at the end of the reaction without being used up. They return in the same form they started the reaction with. So here, since both chlorine free radical and ozone are both gases, then here we call it a homogeneous catalyst. The net reaction, of course, is that 2 moles of ozone decompose into 3 moles of oxygen gas. So the ozone is destroyed by the action of the chlorine free radical. Another example of homogeneous catalysis is the reaction that takes place between the peroxodisulfate ions with the iodide ions to form sulfate ions plus iodine aqueous. Now, as you see here, all the reactants are in the form of aqueous solutions, peroxodisulfate and iodide. And if we look at this reaction, we will see that this reaction cannot happen at all by itself. It must need a catalyst. It cannot take place without a catalyst. Do you know why this is the fact? Why this fact is for? Why this reaction cannot take place without using a catalyst? Do you know?
No, مش remember.
Okay, it's nothing to be remembered, but from the equation, can you deduce why this reaction cannot be formed by itself? You see here the peroxodisulfate and the iodide ion carries, both of them carries negative charge. And we said that the collision theory stated that for any reaction to take place, the reactants must collide together. Can these 2 ions collide together?
No, because they're both negatively charged.
Yes, excellent. That's what you said is excellent, because both of them carries a negative charge. And this means that whenever they approach each other, they will repel because both carries the same charge. That's why this reaction will not happen without a catalyst. But on using a catalyst like the iron plus 2 catalyst, then here the iron plus 2 is in a reduced form and the peroxide disulfide is an oxidizing agent. So at the beginning, it's going to oxidize the iron plus 2 to iron plus 3, and itself will be transferred into the sulfate, which is one of the products. And then the iron plus 3 will react with the second reactant, which is the iodide, and being reduced into iron plus 2 and iodine, which is the second product to be formed, is formed. So here, the iron plus 2 is our catalyst. We started with iron plus 2 and we ended up also with iron plus 2. So it's the catalyst. Whenever something enters and comes out at the end of the reaction without being used up or without being changed in its usual form, then it's a catalyst. But this doesn't mean that it didn't take part inside the reaction. No, it took part, where iron plus 2 was oxidized to iron plus 3, and then in the second step, it was reduced back into the iron plus 2. So this is the catalyst, and it's a homogeneous catalyst because it's in the same phase as the reactants. The reactants are in aqueous state, and the iron plus 2 is also in the aqueous state. So these are different examples of homogeneous catalysts where the catalyst has the same phase as the reactants. Now, the second type of catalysts are the heterogeneous catalysts. And heterogeneous means that the catalyst has a different phase than the reactants. And of course, we've studied in O-level and also in the AS, we had the Haber process in the formation of ammonia. And we have the contact process for the formation of sulfuric acid. In the Haber process, we know that hydrogen gas reacts with nitrogen gas to form ammonia gas. And we said that we use iron as a catalyst. And iron here is in the form of a solid. So it's in a different phase than both reactants. Both of them are gases, but the catalyst iron is in the form of a solid. And also in the contact process, the equilibrium step where sulfur dioxide reacts with half oxygen. Of course, sulfur dioxide is a gas and oxygen in a gas to form sulfur trioxide gas. This is a step in the contact process where sulfuric acid is produced. We use vanadium 5 oxide solid as a catalyst. So in these two reactions, we have the catalyst in a different phase than the reactants. Now, inshallah, we are going to study this reaction in more details in the chapter of transition elements, because we will find that vanadium 5 oxide is a solid, but although it is a solid, it's going to change its oxidation state during the reaction. So during this reaction, we will find that the catalyst has a function to do. It reacts as a catalyst, but itself is going to be reduced and then oxidized back into the vanadium 5 oxide during the reaction. But here the iron reacts in a different way. It's also a homogeneous catalyst, but it behaves in a different way in this reaction of hydrogen and nitrogen. We will find that iron is acting as a solid catalyst. You will see that if this is the iron surface, of course, iron is a metal, and we know that metal, the bonding in metals means that we have layers of positive ions, and then there are free electrons moving inside in between the layers of positive ions. But this is the iron, the solid iron, and then we have the reactants, the nitrogen molecule, and we have the hydrogen molecule. So what happens here is that the hydrogen molecule, together with the nitrogen molecule, at the beginning, they are adsorbed at the surface of the iron. They are going to be adsorbed. They are going to stick here at the surface of the iron. And we will see that as hydrogen is a small atom, it consists of small atoms, of hydrogen atoms, then this hydrogen will enter through the interstitial positions between the positive ions of the iron. The hydrogen is going to go through these pores or these three holes in between the positive ions of the iron and form what we call a hydride. It forms what we call a hydride. It means that the hydrogen atoms are going to go through and are going to be placed in between the positive layers of the iron solid. We call it interstitial hydride. Interstitial means that the hydrogen goes in between the positive ions here and held together with the iron. And so when this hydrogen atom is held in between the positive ions, and as nitrogen molecule is also adsorbed means sticks at the surface of the iron metal, then it will be near the hydrogen atoms that are now found in between the positive ions of the iron. So they are going to react together. So the second step is to react the hydrogen atoms together with the nitrogen atoms. They are going to react, of course, when nitrogen is also adsorbed at the iron surface. This means that this bond is going to be weakened. And so now we have hydrogen atoms and we have nitrogen atoms. So they react together to form the ammonia. And then the third step is to dissolve away from the iron. When ammonia is formed, when hydrogen and nitrogen react together and ammonia is formed, then it's going to be dissolved away from the iron metal. So if the iron, like here, if the catalyst is acting as a solid, not that in case of vanadium 5 oxide, we said that in vanadium 5 oxide in the contact process, there will be an exchange of oxidation states. The vanadium 5 oxide is going to be reduced and then oxidized during the reaction. But here the iron is not going to be reduced nor oxidized. It will remain the same as iron, but what happens is that the reactants, which are the hydrogen molecules and the nitrogen molecules, are going to be adsorbed at the surface of the iron. And then the small hydrogen atoms are going to pass through the positive ions of the iron metal, and it forms what we call an interstitial hydride. And then the hydrogen atoms will react with the nitrogen atoms that are also now adsorbed at the surface of the iron. And then they are going to react together, forming the ammonia. And then the ammonia will desorb away from the iron metal. So 3 steps takes place whenever a catalyst is acting as a solid. Of course, if the surface of the iron is completely filled with hydrogen and nitrogen gases, then no more space is found. So we will find that the rate after some time will not change. The iron at the beginning will increase the rate of the reaction because this happens. It weakens the bonds between hydrogen molecules and nitrogen molecules, allowing them to react together. So as long as they are found at the surface of iron, they fill the surface of the iron. So if more hydrogen and nitrogen molecules are near, they will not be able to be adsorbed at the surface of the iron because all the surface is already covered by hydrogen and nitrogen. So we will find that the rate will not increase more. It will increase to a certain extent and then will not increase more even if we increase the pressure. That's because the surface of the iron is completely filled with other molecules of hydrogen and nitrogen, and there is no space for more hydrogen and nitrogen to come in contact with the iron and form the product. Understand, or shall I repeat anything?
Understood.
Okay, thank you. Now we come by what we call autocatalysis. Now, what do we mean by autocatalysis? Sometimes in some reactions, we will find that one of the products is acting as a catalyst. We don't have to put a catalyst inside our reaction for the reaction to be faster. But sometimes one of the products is a catalyst by itself. That's why we call this reaction at which one of the products is a catalyst, we call it an autocatalysis reaction, or autocatalysis takes place in this reaction. Auto, of course, means by itself. For example, if we take this reaction, ethane dioic acid, when we titrated with potassium manganate in presence of an acid medium to form carbon dioxide, manganese, and water, we will find that this reaction is very, very slow at the beginning. Here we put the ethane dioic acid in a conical flask, and this is the ethane dioic acid. We put it in the flask and we titrated with potassium manganate. We know that potassium manganate is purple in color, and it is supposed that whenever we add drops of potassium manganate to ethane dioic acid and a redox reaction takes place between them, we will find that the drop, we should have found that any drop of potassium manganate coming down here on ethane dioic acid, its color disappears, because a reaction will take place between the potassium manganate and ethane dioic acid and to form the manganese Mn+2. So any drop that is added, its color should be removed until at the end point, any drop added from potassium manganate will remain as it is here, as all the ethane dioic acid will be finished. And we find that the end point is that a pink color is formed here in our solution. This reaction is taking place. It's a redox reaction, and it's a well-known reaction, but we will see that at the beginning of the reaction, this reaction is very, very, very slow. But as manganese Mn+2 is formed, this is our catalyst. One of the products is our catalyst here. So at the beginning, there was no Mn+2, or even a very small amount of it was present. So the reaction is very slow. But as more and more manganese +2 is formed, it will act as an autocatalyst. It catalyzes the reaction, and we will find that the speed of the reaction will increase until, and of course, it will increase at the beginning, but at the end, as any normal reaction, the rate decreases because the concentration of ethane dioic acid decreases with time. So you will see that at the beginning, we said that this reaction is very, very slow reaction. That's why if we draw the concentration of the reactant against time, we will find that the reaction rate at the beginning is very slow, because manganese +2 is either not found at the very beginning, or else it is found in a very small amount at the start of the reaction. So it's not reacting as a catalyst at the beginning. And the reaction is very, very, is having a very, very slow speed. But as manganese +2 starts to form in a certain amount, it will act as an autocatalyst. And so we will find that the reaction will speed up here in this part. And then, as usual, as ethane dioic acid is being consumed, we will find that the rate decreases with time until it eventually here stops. So any normal reaction, in any normal reaction, the reaction, we said that if we draw the concentration of the reactants against the product, we said that the reaction starts with a high speed, and then the rate decreases with time until it stops. So this is the start of any normal reaction. But in case of the reaction between potassium manganate and ethane dioic acid, we said that the reaction at the beginning is a very, very slow reaction, so as if it is not happening. And then as Mn+2 starts to form, which is one of our reactants, as it starts to form, it will act as an autocatalyst. And autocatalyst means that itself will speed up the reaction. So you will see here that the reaction speeds up and then starts to decrease once more as ethane dioic acid concentration decreases in the reaction mixture. It decreases until it stops here. Okay. Do you have any question here? Because these parts sometimes come in exams. Sometimes they bring such a thing in exams. So do you have any question concerning this part?
No.
Okay. Now we want to know the effect of temperature on the rate constant. Now, of course, we said that we studied before the collision theory, and the collision theory stated that as the temperature increases, what happens to the rate? If we increase the temperature, what happens to the rate?
If you increase the temperature, the rate of the reaction increases.
Yes, excellent. Why? Why does it increase? Excellent.
Because the temperature increases the kinetic energy, thus the molecules move faster in successful collisions.
Yes, excellent. So as the temperature increases, more number of frequency of collision increases between the particles. This is one thing, but this is not the most important thing. The most important thing, as you mentioned, that as the temperature increases, the kinetic energy of the particles will increase, and so they will collide together with energies equal to or greater than the activation energy for the products to be formed. So we want to find out the relation between the temperature and the rate constant. Now, we said that there is an equation that is called the Arrhenius equation. Of course, this Arrhenius is a scientist, a Swedish scientist, who found out the relationship between temperature and the rate constant K. He made up his equation that says that the rate equation, the rate constant K equals AE to the power minus E over RT. The rate constant K equal AE to the power minus E over EA. Of course, this is the activation energy over RT, where K is the rate constant and EA is the activation energy, R is the gas constant, T is the temperature in Kelvin. Now, what is A? A, we call it a pre-exponential factor. Now, what is this constant? This is a constant, of course, or we call it the pre-exponential factor, which is a measure of the rate at which collisions takes place between particles irrespective of their energy. It means that even if any two particles collide together, even not with enough energy to form the product, then the pre-exponential factor accounts for this collision. It's a measure of this collision between particles, even the rate at which the particles collide together, even if they don't have enough energy to form the product. And also, it shows us how molecules, inside it, there is the factor of how molecules are oriented with respect to each other when they collide. Because as you remember in the collision theory, that it's stated that for any reaction to take place, molecules must collide together and they must have a certain orientation by which when they collide, they can form the product. And of course, the energy, which is that they must have energies equal to or greater than the activation energy. So the pre-exponential factor here, A, accounts for two things. Accounts for the rate of collision between particles, even if they do not have the energy enough to form the product, and also accounts for the orientation of the molecules at the time they collide together. So this is the pre-exponential factor A. So the rate constant K equals A e to the power minus EA, which is the activation energy, times R, which is the gas constant, and T, which is the temperature in Kelvin. So if we take the ln of both sides, you know the ln is like the logarithm, but it's called ln. It's the logarithm to the base 2.303, to the base 10, sorry. Yani if we want to change the ln to the log, these are mathematical functions. You will find them on your calculator. So if we want to change from ln to log, we multiply by 2.303. And these are mathematical functions. So if we take ln of both sides, so ln k equal ln A, and then ln and E cancel each other. So we get minus EA over RT. We are going to take ln both sides. So it's ln K equal ln A plus ln E to the power minus E over RT. When we have ln and E beside each other, they cancel each other because they are opposite to each other. And we are left with this part, which is minus EA over RT. So ln K equals ln A minus EA over RT. So if we draw a plot between ln K and minus, we don't, of course, draw minus, but we draw the relation between ln K, which is ln the rate constant, against 1 over T. If we plot such a plot, we will get a straight line with a negative slope or negative gradient, and the slope equals, or the gradient equals, minus EA over R. Of course, our slope will be negative. So if we calculate this gradient or this slope, we get a negative value because the straight line will be in this way, coming from left to right, downward. So it's with a negative gradient. And this negative gradient equals minus EA over R. So if we know the slope or the gradient of the straight line by drawing ln K against 1 over T, we get a slope of negative charge. So this slope equal minus EA over R, from which we can calculate the activation energy of this reaction. And it usually comes in the exams, as we are going to see when we solve past papers. Okay, so the relation between the rate constant K and the temperature T was done by a scientist who was called Arrhenius, and he postulated his equation, Arrhenius equation, which showed us the relation between the rate constant and the temperature, where ln K equals ln A minus EA over RT. So if we plot ln K against 1 over T, we get a straight line with a negative gradient, and this gradient equal minus EA over R. And the part that is, if we extrapolate this line, the part that it crosses the y-axis or the ln K axis is the ln A. It gives us the pre-exponential factor. They usually bring such a problem in exams, and we are going to see now an example how to solve such a problem. It's very easy, and they usually give you this equation or that equation. They give it to you in the exam. All you have to do is to plot what the values they give you for K and for 1 over T, and from which you can calculate the activation energy. Okay. Do you have any question here? Of course, we are going to see now a problem.
Yes.
Okay. So this is a worked example to be applied on this Arrhenius equation. It says table A shows some data related to the reaction between peroxide disulfate and iodide ions in aqueous solution. He gave us this equation, and he stated that at temperature 300 Kelvin, the rate constant was found to be 0.00513, and at 310 Kelvin, it was found to be 0.00833, and so on. He gave us some temperatures and the magnitude of the rate constant K, and he wants us to calculate the activation energy of this reaction. So all we have to do here is to apply Arrhenius equation. To apply Arrhenius equation, we know that Arrhenius equation stated that ln K equal ln A minus EA over R times 1 over T, EA over RT. So if we plot ln K against 1 over T, we are going to get a straight line with a negative slope, which is equal to minus EA over R. So all we have to do here is to take the reciprocal of the temperature K the reciprocal of the temperature T in Kelvin. So here 1/T, we take the reciprocal of 300 to be 0.0033 and so on. We take the reciprocal of these temperatures and we calculate the ln of this K value. And then we are going to draw or plot a curve between ln K against 1/T. If we calculated 1/T, we get it 0.003 till 0.009. This is these values of 1/T. This is 1/T. And ln K, all of it is negative. That's why it's drawn in this way, downward. And so if we take the values of ln K against 1/T, we got a straight line with a negative slope. Now, we want to calculate the gradient of this line, because the gradient is equal to minus EA/R. So we are going to take any two points on this straight line to calculate the gradient. And of course, they shouldn't be too near to each other. And also, they shouldn't be too far away from each other, because I've noticed that in the mark scheme, if we take a big difference between these 2 points, for example, if I want to take this point and that point, we will find that our results are not coincident with the results in the mark scheme. So usually don't take too near points and don't take too far points. Take it a little bit here and there to get a good result. Take the points far away, but not too far away from each other. So here, for example, if we want to calculate the gradient, they took minus 3.5, this point, and minus 5.27. 5.27, it's here, I think. Okay, so minus 3.5 minus, and then minus 5.27 divided by 0.00. This is 0.00033. No, this is 0.00294, and this is the 0.0033. You get the gradient equal minus 4538. This is the gradient. And we said that the gradient equals, this is equal to 538 minus 4538. The minus will go with the minus. And to find out the activation energy, we have to multiply the gradient we got times the gas constant, which is 8.31. So we get the activation energy in joules per mole. And of course, it's a big value. That's why we have to change it into kilojoules per mole by dividing it by 1,000. Now, as you are going to see when we are solving past papers, that usually they bring such a problem at the end of the question of kinetics, of course. Okay. Do you have any question here?
Yes.
Okay.